Right now, our entire solar system is falling sideways through the Milky Way at 500,000 miles an hour. And almost everything you've ever seen of it is a lie flattened onto a page. Above us hangs a frozen sphere of 1 trillion comets. Below us, a galactic ocean drops away into nothing. Today we leave the pancake. We climb to the icy ceiling of the sun's kingdom, plunge beneath the planets toward the galactic south, and meet the visitors falling on us from directions no map ever showed you. If wonder still moves you, hit subscribe, look up, we begin. Open any school textbook and you see the same picture, a yellow sun, 8 planets in tidy rings, everything sitting on one neat page, like marbles on a tabletop. That picture has been burned into your mind since you were a child, and it is wrong in a way that should make you uncomfortable. Space has no tabletop, there is no floor, there is no ceiling. The page is a trick your brain plays, so the numbers stay simple. In reality, the sun and its planets float inside a 3-dimensional ocean, with emptiness stretching above your head and below your feet in directions that have no name. So why does every diagram still look flat? Because it almost is. The planets really do orbit close to a single shared plane, called the ecliptic. Picture a giant invisible dinner plate with the sun at the center and the planets sliding around its rim. Earth sits on that plate, Jupiter sits on that plate, even distant Neptune barely tilts away from it. The plate is real. The lie is pretending nothing exists off the plate. Above and below this thin disk, the universe keeps going. There are objects, forces, currents, and whole regions that never appear in your textbook because they refuse to lie flat. Some of them are bigger than the planets. Some of them are older than the Sunday. Some of them are falling toward us right now from angles no spacecraft has ever photographed. Here is the part that breaks the picture for good. Our solar system itself is tilted. The plate of the planets sits at roughly 60 degrees relative to the much larger plate of the Milky Way galaxy. Imagine a frisbee resting at a slant inside a much wider frisbee. We are spinning sideways inside a galaxy that is spinning a different way entirely. Nothing about our position is square, nothing about it is level, and we are moving. The whole solar system is drifting slowly toward what astronomers call the galactic north, climbing roughly 7 kilometers every second above the central plane of the Milky Way. That motion is not in any textbook either. Right now, as you breathe, the sun is rising, slowly, across millions of years, but rising. So when you look up at a clear sky and see the band of the Milky Way stretching overhead, you are seeing a slice of the bigger plate from inside the smaller one. The two are not aligned. They never were. The diagram was a comforting cartoon for children who needed planets in a row. What waits in the directions the cartoon erased is stranger than fiction. There is a frozen wall of comets 1,000 times farther than Pluto. There is a tear in the gas of our galaxy that we are passing through right now. There is a current of stars sliding past the sun in the wrong direction. There are visitors from other star systems entering through our roof and exiting through our floor, leaving us nothing but a puzzle. The flat picture of the solar system is over. From this point on, you need to start thinking in spheres, in shells, in tides, in tilts. Hold that thought, because the first thing waiting for us above the planets is a swarm so large it could fit 1 trillion mountains, and almost no one has ever seen a single piece of it. If you flew straight up from the North Pole of Earth, away from the page of the solar system, what would you hit first? Nothing for a very long time. You would pass the moon in a few hours. You would pass Mars in months. Jupiter would slip away beneath you in a couple of years. Neptune, the last true planet, would drift below you after about a decade of travel at rocket speed. You would feel like you had reached the edge of everything. You would barely have started. Past Neptune sits a thin ring of icy worlds called the Kuiper Belt. Pluto lives there, along with thousands of frozen siblings. The belt is wide, but it is still mostly flat, still hugging the same plate as the planets. After it comes the scattered disk, where the orbits start tilting more wildly. And then, farther still, far past anything any human has ever sent a probe near, you would meet something most people have never even heard the name of. A wall, not a solid wall. A wall made of ice. Astronomers call it the Oort cloud, named after the Dutch scientist who proposed it in 1950. It is not a belt. It is not a ring. It is a sphere. A gigantic frozen shell wrapped completely around the sun and every planet, including the empty space above and below the ecliptic plate where nothing else lives. Picture a dandelion seed head, with the sun as the tiny center and a fluffy cloud of icy spheres surrounding it on every side. That is the shape. The numbers behind that shape are almost cruel. The inner edge of the Oort cloud is thought to begin somewhere around 2,000 times farther from the sun than Earth is. The outer edge may stretch 100,000 times farther. To put that in human terms, light from the sun takes about 8 minutes to reach your face. Light from the sun takes more than a year to reach the outer edge of the Oort cloud. Voyager 1, the fastest object humanity has ever launched, will need roughly 300 years just to touch the inner edge. It will need 30,000 more years to fly through. Inside that shell, scientists believe, drift trillions of frozen objects, mountains of ice, boulders of frozen methane, and ammonia and water. Some are the size of small cities. Some are the size of small countries. They are spread so thinly that if you were standing on one of them, the next one would be tens of millions of miles away. A faint speck against a sky so dark the sun itself looks like a bright star with no disk at all. This is the true outer skin of our solar system, the real boundary, the place where the sun's gravity finally gives up and the pull of the rest of the galaxy starts to win. Cross it, and you are no longer in our system. You are in interstellar space. And here is the unsettling part. We have never seen the Oort cloud directly. Not one telescope has photographed a single confirmed member of the outer shell. We only know it is there because something keeps falling out of it, plunging down through the ceiling of the planets, burning bright enough to write its name in our skies for thousands of years. How can something be everywhere around our sun, hold 1 trillion objects, and still be invisible? The answer is darkness. The Oort cloud is the deepest darkness in our solar system. Out there, the sun is just one star among many. The light is so weak that an iceberg the size of Manhattan would shine fainter than a candle seen from the moon. Our telescopes simply cannot pick out something that dim, that small, and that far. So scientists work in reverse. They watch what comes back to us. Long-period comets, the kind that take thousands or even millions of years to complete a single orbit, fall into the inner solar system from every direction at once. Some come from above the planets. Some come from below. Some scream in sideways at angles no planet has ever known. Plot those orbits on a map, and the points of origin form a sphere. That sphere is the Oort cloud, drawn by its own escaping children. The shell is not uniform. Astronomers believe it has 2 layers. The inner layer, sometimes called the Hills cloud, is shaped more like a thick, puffy donut, still slightly aligned with the plane of the planets. The outer layer is the true sphere, wrapping the entire system in every direction. The outer layer is thought to be the source of comets that arrive from impossible angles. The inner layer is thought to be a quieter reservoir, slowly leaking new comets outward to refill the sphere as it loses its weakly bound members to the dark. Now, picture the size. The inner Oort cloud begins at a distance of perhaps 2,000 astronomical units. The outer Oort cloud may stretch to 100,000. That outer edge sits roughly halfway to the next star. Halfway. Our solar system is so large that its frozen skin almost touches the frozen skin of our nearest stellar neighbor. If 2 such shells were ever to overlap, comets from both stars could mingle and trade. There may already be visitors mixed in. Some scientists suggest the sun captured icy bodies from sister stars when it was young and crowded inside a stellar nursery. If that is correct, then a fraction of the comets in our outer shell were never born around our sun at all. They are quiet refugees from systems we cannot identify, sitting silently above and below us, waiting their turn to fall. The mass of the entire shell is still uncertain. Estimates suggest the Oort cloud holds enough material to build several Earths, scattered across an unimaginable volume. That is a few Earths' worth of ice spread across a bubble more than a light-year wide. The density is nearly nothing. A spaceship flying through it could pass for 1,000 years and never see a single object. And yet the shell is not still. The Oort cloud is alive in a slow and frightening way. Passing stars tug on it. Giant clouds of gas in the galaxy disturb it. The galaxy itself stretches it. Every disturbance can knock loose a frozen mountain and send it falling toward the sun, sometimes taking hundreds of thousands of years to complete the plunge. What happens when one of those mountains finally arrives is something humans have watched for as long as we have had eyes pointed up. A long-period comet does not sneak in. It announces itself. For most of its life, a comet from the Oort cloud is a silent rock of ice drifting in the deep dark, far above or below the planets, locked in an orbit so slow that one full lap takes longer than the entire history of the human species. Then, something jostles it. A passing star, a ripple in the galaxy, a bump from a sibling. The orbit shifts by a hair, and the comet starts to fall. Falling toward the sun from such a distance is an enormous journey. The comet picks up speed slowly at first, the way a marble released at the top of a long ramp barely moves before it accelerates. By the time it crosses the orbit of Neptune, it is moving fast. By the time it reaches Jupiter, it is screaming. By the time it whips around the sun, it can be traveling tens of miles every second, faster than anything humans have ever built. The sun does to this frozen mountain what a campfire does to ice. The surface boils, gas and dust explode outward. A glowing head forms around the dark nucleus, sometimes 1,000,000 miles wide. Behind the comet, two tails unfurl, one blue and straight, made of charged gas pushed by the sun's wind, one curved and yellow-white, made of dust pushed by sunlight itself. Both tails point away from the sun, no matter which way the comet is flying. This is when humans see it. Two of the most beautiful examples in living memory came from the Oort cloud. Comet Hyakutake passed close to Earth in 1996 and stretched across nearly half the sky as a glowing blue-green sword. Comet Hale-Bopp arrived a year later, bright enough to see for 18 months in a row, even from inside a city. Both fell from above the plane of the planets. Both came from directions no normal comet should have come from. Both will return. Hale-Bopp is expected back in roughly 2,500 years. Hyakutake will not be seen again for tens of thousands of years. Here is the part that quietly disturbs astronomers. These visitors do not respect our pancake. A short-period comet, born in the Kuiper belt, almost always travels in the same direction as the planets and stays close to the same plate. A long-period comet does whatever it wants. It can plunge from straight above. It can climb from straight below. It can orbit backwards, sliding around the sun in the opposite direction of every planet, like a single car driving the wrong way down a freeway full of traffic. That backwards motion is a fingerprint. It tells scientists the comet was knocked loose from the spherical outer Oort cloud, where every direction is equally allowed. Out there, the rules of the planets do not apply. Up and down, clockwise and counterclockwise, all of them are the same. Each new long-period comet is a piece of evidence. A mountain mailed down to us from the frozen wall above and below. A sample we did not have to send a probe to collect. We just had to wait. And the wait is about to get more interesting, because not every visitor that falls through our roof was born here at all. In October of 2017, a telescope in Hawaii caught something nobody was supposed to see. A small dot of light, traveling too fast. Far too fast. The sun's gravity pulls every comet, every asteroid, every planet into a closed loop. You go around, you come back. That is the rule. This dot was not on a closed loop. It was on a path that opened outward, like an arrow shot through our system from one side to the other. Whatever it was, it had not started here, and it was not staying. They named it Oumuamua, a word that means scout or messenger. It was the first object ever confirmed to come from another star. It arrived from above. Specifically, it dropped down toward the plane of the planets from the constellation of Lyra, plunged through, and is now climbing out the other side, vanishing into the dark of the southern sky. We had 11 days of good observation. Then it was gone forever. What we saw in those 11 days made no sense. Oumuamua was shaped, by best estimate, like a long, thin shard, possibly 10 times longer than it was wide, tumbling end over end as it flew. It reflected light unevenly, like a dark rock with shiny patches. It accelerated slightly as it left the inner solar system, as if something was pushing it from behind, but no comet tail was visible, no glow, no outgassing seen. Theories piled up. A nitrogen iceberg from a faraway world, a piece of a shattered planet, a hydrogen splinter from a stellar nursery. A few astronomers suggested, controversially, that it might have been a piece of alien technology. Most disagreed. We will never know which theory was correct. Oumuamua is too far gone to study. Its true nature is locked outside our reach, falling through the night between the stars. Then, almost as if to remind us we were not imagining things, a second visitor arrived in 2019, Comet Borisov. This one was clearly a comet, with a fuzzy head and a real tail, and its path showed without a doubt that it had been falling between stars for billions of years before brushing past our Sunday. It dropped into our system from above the plane and exited below, taking another piece of another star system with it. A third visitor showed up more recently, an interstellar object catalogued under a complicated name and tracked into our system from a completely different direction. Each one of these objects entered our pancake from outside the page. Each one passed through the empty space above or below the planets, the very space that older textbooks treated as if it did not exist. This is the disturbing implication. The space above and below our solar system is not empty. It is a busy hallway. Pieces of other stars are passing through it constantly. We only saw 3 because our telescopes only recently became sharp enough to catch them. There may have been thousands more before we could see them. There may be a dozen passing through right now. Some might have already been pulled into orbits we cannot trace. Some might have struck a planet long ago. The roof and the floor of our solar system are leaking in both directions, and nothing about that flow ever stops. Step inside the orbit of Pluto for a moment and look at the sun differently. The sun is not just a glowing ball. It is a giant balloon, constantly inflating. Out of its surface streams a hot wind of charged particles, racing outward in every direction at roughly 1,000,000 miles an hour. This is the solar wind. It does not care about up or down. It does not respect the plane of the planets. It blows in a sphere, washing over everything, including the empty spaces above and below the page. That wind has to stop somewhere, and it does. Far past Neptune, it slams into the thin gas that drifts between the stars. The interstellar medium, the collision creates a soft boundary, a great rounded shell where the solar wind finally loses its push. Astronomers call this shell the heliopause, and the entire bubble inside it is called the heliosphere. The heliosphere is the sun's true territory. Everything inside it is bathed in its wind. Everything outside it belongs to the wider galaxy. The shape is strange. The heliosphere is not a perfect sphere. It is more like a comet, with a rounded nose facing the direction the sun is moving through the galaxy, and a long tail trailing behind. We are flying through the local interstellar gas at roughly 50,000 miles per hour, and the gas pushes back, squashing the front of the bubble and stretching the back. From above, the heliosphere would look like a giant, glowing teardrop, with the sun and all the planets nestled near the front. How big is this bubble? The boundary on the upwind side sits roughly 120 times farther from the sun than Earth. On the downwind side, the tail may stretch many times longer. That means even the closest edge of our sun's bubble is far past Pluto, far past the Kuiper belt, deep in the territory where the Oort cloud begins. In 2012, Voyager 1 became the first human object to pierce the heliopause and step outside the bubble. 6 years later, Voyager 2 followed. Both probes were launched in 1977, when the people steering them were younger than most cars on the road today. Both crossed the bubble at slightly different distances, proving that the heliopause is not a smooth wall but a wrinkled, shifting membrane that breathes. Above the planes of the planets, the heliopause is closer in some directions and farther in others. Below the planes, it dips and bulges in patterns that scientists are still mapping. The bubble does not match the disk inside it. It is its own three-dimensional skin, indifferent to the flat orbits of Mercury or Saturn. Here is why the bubble matters to you. Everything outside the heliopause is hostile. Cosmic rays from distant exploding stars stream through the galaxy at almost the speed of light. Many of those rays would shred unprotected DNA. The sun's wind deflects most of them, like an umbrella against radioactive rain. Without the heliosphere, life on Earth would face a sky full of invisible bullets every second. Above us and below us, the umbrella holds. Beyond it, the storm is constant. The next thing you need to know is that the storm has a current, and our sun is sailing right through one of the strangest currents in this corner of the Milky Way. Outside the bubble, the sun is not alone in empty space. It is sitting inside a fog. That fog has a name, the local interstellar cloud. Astronomers sometimes call it the local fluff. It is a soft puff of warm hydrogen and helium gas, stretched roughly 30 light-years across, drifting through the galaxy on its own slow current. Our entire solar system is buried inside it. The sun has been moving through this fluff for tens of thousands of years and will keep moving through it for tens of thousands more. The cloud is thin, so thin you would never see it with your eyes. There are only about a quarter of a hydrogen atom in every cubic centimeter of space, which is a vacuum compared to the air you are breathing. But it is not nothing. It pushes against the sun's bubble. It glows faintly when telescopes look in ultraviolet. It carries dust, grains, magnetic fields, and slow-moving cosmic rays. The strange part is what surrounds the fluff. The local interstellar cloud is itself floating inside a much bigger bubble of even thinner, hotter gas, called the local bubble. The local bubble is roughly 1,000 light-years across, and it was carved out of the galaxy by a string of supernova explosions millions of years ago. Several giant stars went off in succession, blasting their material outward, and the shock waves cleared the area like a snowplow clears a parking lot. What was left behind was an oddly empty zone of hot, low-density gas, with a few smaller, cool clouds scattered inside it. Our sun is one of those scattered guests. We do not own the bubble. We are passengers passing through it, drifting from one cool cloud toward another. In a few thousand years, the sun is expected to leave the local interstellar cloud entirely and enter a slightly different one called the G cloud. It will be like sailing from one patch of fog into a slightly thicker patch. Why does this matter? Because the cloud we are sailing through directly affects the size of the sun's heliosphere. When the cloud is denser, it presses harder on our bubble, shrinking it. When the cloud is thinner, our bubble can expand. Above and below the planets, this expansion and shrinking is happening constantly. On timescales humans cannot feel, but stars can. There is a haunting hint in the geological record. Some scientists have proposed that, long ago, our solar system may have passed through a much denser cloud, one thick enough to compress the heliosphere down to inside the orbit of Earth. If true, it would have stripped away part of our planet's protection from cosmic rays. Sediment from millions of years back contains a strange spike of a rare isotope of iron, an isotope that forms in supernovae. That spike fell from somewhere. Many think it fell out of a passing dense cloud, raining material onto the early Earth from above. The local bubble is not the end either. Outside it, deeper into the galaxy, sits an even larger network of structures. Hot tunnels carved by older supernovae, cold rivers of dense molecular gas where stars are still being born, filaments and sheets that span thousands of light years, all of them invisible to the naked eye, all of them pressing on the bubble that protects us. We are floating in a sea full of weather, and the next current is even stranger. Step back even farther. Forget the sun, the planets, the bubble, the cloud. Look at the whole galaxy. The Milky Way is a flat disk, roughly 100,000 light-years across, and only about 1,000 light-years thick. Inside that disk live 200 to 400 billion stars, plus rivers of gas, banks of dust, and a swirl of dark matter binding it all together. From far above, it looks like a glowing pinwheel with arms. From inside, it looks like a fuzzy band stretched across the night sky. That band is what you see on a dark summer night when people say they can see the Milky Way. You are looking edge-on through your own galaxy. There is a thin, invisible plane that runs through the middle of the disk, the galactic equator. Every star, every cloud of gas, every spiral arm tries to cling close to that equator, the way every planet in our solar system tries to cling close to the ecliptic. Move away from the plane, and the population of stars thins out fast. Here is where our cozy picture gets tilted. Our solar system does not sit on the galactic plane the way we sit on the ecliptic. We sit slightly above it, perhaps 50 to 100 light-years above, and the entire flat plate of the planets is angled at roughly 60 degrees compared to the flat plate of the galaxy. The two pancakes are not stacked, they are crossed. That tilt is responsible for one of the most beautiful illusions in the night sky. When you see the band of the Milky Way stretching from horizon to horizon, you are looking along the galactic plane. When you see the planets walk in a line across the sky, you are looking along the ecliptic. The two lines cross on the dome of stars, making an X over your head. They were never meant to match. Our sun is also moving through this big disk on a long, slow orbit. One full lap around the center of the Milky Way takes between 225 and 250 million years. Astronomers call that one galactic year. The dinosaurs lived almost an entire galactic year ago. The first single-celled life on Earth has been around for roughly 20 galactic years. Each lap, the sun and its bubbles sweep through different neighborhoods of the galaxy, different clouds, different stellar densities, different radiation environments. And the orbit is not flat either. Like a horse on a carousel, the sun bobs up and down through the galactic plane as it goes around. It dips below, climbs back to the middle, rises above, falls back, and crosses the plane again roughly every 26 to 30 million years. We are above the plane right now, climbing slowly higher. Some scientists have suggested that these crossings of the galactic plane might line up with mass extinctions on Earth, perhaps because the sun passes through denser clouds during them, jostling comets out of the Oort cloud. The idea is unconfirmed, even controversial, but the bobbing motion itself is beyond doubt. We have measured the sun's vertical velocity. We are moving up. All of this is happening above and below the disk of the planets, in directions almost no diagram bothers to draw. The next layer we need to peel back is older, darker, and far emptier than the disk itself. Above and below the galactic plane, the disk thins out fast. Stars become rare. Gas becomes rare. By the time you climb 1,000 light-years above the central pancake, you are leaving the busy part of the Milky Way entirely. You are not leaving the galaxy. You are entering its halo. The galactic halo is a vast, rounded region wrapped completely around the disk, top and bottom, side to side. Imagine a glowing fried egg. The yolk is the bulge at the center. The white is the disk. The halo is the invisible bowl of air around the egg, filling the space above the yolk and below the white in equal measure. Our Milky Way has one of these halos. So does every spiral galaxy. The halo is mostly empty, but not completely. Three things live in it. The first are old, lonely stars, scattered far above and below the plane, drifting through the dark. Many of them are among the oldest stars in the Milky Way, formed when the galaxy was young and chaotic. before the disk settled into its tidy shape. A halo star can be 12 billion years old, almost as old as the universe itself. They orbit the galaxy on long, plunging paths, diving through the disk and rising back out, indifferent to the rotation that keeps the rest of the stars in line. The second are globular clusters, tight balls of 100,000 to 1 million stars, packed so closely together that, if you lived on a planet inside one, the night sky would burn with thousands of suns, and there would be no true darkness. The Milky Way has roughly 150 of these clusters. Most of them orbit the galaxy outside the disk, looping above and below the plane on huge, slow paths. Some take 1 billion years to complete a single lap. The third is a faint, glowing soup of ionized gas, far thinner than the gas in the disk, hotter, and almost impossible to see. This hot halo gas may stretch out hundreds of thousands of light years from the center, encasing the entire disk in a gentle whisper of plasma. And there is something else hiding in the halo, something invisible, something that does not glow at all, does not absorb light, does not interact with ordinary matter except through gravity. We call it dark matter. Most of the Milky Way's mass appears to be made of it, and the halo is where most of that mass lives. It is everywhere above us. It is everywhere below us. Right now, dark matter is flowing through your body, through this room, through the planet, and you cannot feel it, because it does not push on the atoms you are made of in any way you can detect. The halo above and below the galactic disk is also where the galaxy meets its visitors. Old stars stripped from smaller galaxies the Milky Way has eaten. Streams of stars flowing in long ribbons after collisions billions of years old. Whole dwarf galaxies still being torn apart by our gravity, leaving glowing breadcrumb trails through the empty space outside the disk. Look up from the right place at the right time, and you will not see those ribbons with your eyes. But the telescopes see them. They paint the sky above and below us with the wreckage of a dozen older worlds. That wreckage is where the next part of the story begins. The Milky Way is a quiet predator. For most of its life, it has been eating smaller galaxies, slowly, gently, without anyone alive to witness most of it. A small galaxy drifts too close. The Milky Way's gravity grabs it. The little galaxy stretches, distorts, and breaks into a long ribbon of stars. Over hundreds of millions of years, that ribbon wraps around and around the Milky Way's halo, dissolving into the larger galaxy's body. Look above the disk, in the right direction, and you will find one of these meals still in progress. The Sagittarius dwarf galaxy, or what is left of it, is currently being torn apart and pulled around the Milky Way like sweet pasta around a fork. It has already passed through the disk several times. Each pass has stripped away more of its stars. What remains of its core is still there, still recognizable, but a great glowing trail of its lost members now wraps the entire Milky Way in a giant loop, both above and below the plane. That trail is called a stellar stream. Astronomers have mapped dozens of them now, snaking around our galaxy. Each one is the ghost of a smaller galaxy that wandered in too close and was swallowed. Our solar system does not lie inside Sagittarius, but Sagittarius passes nearby in cosmic terms. Some of its stars may already be drifting through our region of space, mixed in with the local stars we always thought were ours. Some of the dust pressing on our heliosphere may have been born in a galaxy we are still in the slow process of digesting. Below the disk, hidden until recently, sits another secret. Astronomers have found evidence that an entire massive dwarf galaxy crashed into the Milky Way roughly 10 billion years ago. They named the intruder Gaia Enceladus, after the European Space Telescope that uncovered the clues. Its remains are now scattered throughout the inner halo, including in the empty space above and below us. A measurable fraction of the older stars near our Sun may once have belonged to that lost galaxy. Their orbits give them away. They are still moving as a group, still carrying the memory of the impact. Here is the unsettling thought. Some of the stars you see on a clear night, the ones that look like familiar specks of light, may not be Milky Way natives at all. They may be alien immigrants from a galaxy that died before life on Earth even began. We have been living among the survivors of a cosmic crash for as long as we have had eyes to look up. The streams keep coming. The sun is currently passing through, or near, several of these ghost ribbons. One of the most striking is called the Helmi Stream, made of stars that move in a strange direction, betraying a different origin. Another is the Sequoia structure, named for an even older intruder. Each one is invisible to the naked eye. Each one is real, mapped by satellites that measured the precise paths of more than 1 billion stars across the sky. Above and below us, the galaxy is haunted by its meals. The dark sky is not blank, it is layered, like sediment, with the corpses of older worlds. And the Milky Way is still eating. The biggest meal it has ever attempted is already on its way. If you could leave the Milky Way and look back at it from far above, you would not see it as the lonely island most people imagine. You would see it as one of 2 main galaxies in a small group, swirling slowly around each other. The other one is bigger. It is also closer than it used to be. Its name is Andromeda. It holds roughly 1 trillion stars, several times more than the Milky Way. It sits about 2.5 million light years away, drifting through the dark just above the galactic plane in our sky. On a moonless night, far from city lights, you can spot it with your bare eyes, a faint smudge in the constellation that gave it its name. You are looking at the most distant object the human eye can naturally see. You are also looking at an oncoming train. Andromeda is not drifting peacefully. It is heading toward us at roughly 250,000 miles per hour. Most galaxies in the universe are moving away from each other, carried apart by the expansion of space. Andromeda is doing the opposite. It is so close and so massive that its gravity has overpowered the expansion. It is falling toward our Milky Way along a long, slow path, and the meeting is set. In about 4 to 5 billion years, Andromeda will not just pass nearby, it will collide with the Milky Way. The 2 giant pinwheels will fly into each other, distort, twist, and slowly merge into a single, larger galaxy that astronomers have already nicknamed Milkomeda. The collision will not be a violent crash like cars on a highway. Stars are so far apart inside galaxies that almost none of them will physically hit each other. It is more like 2 clouds of mosquitoes flying through one another. Most stars will simply pass through the gaps, but the gas clouds in both galaxies will slam together and ignite, triggering a furious wave of new star birth. The night sky on Earth, if anyone is still alive on Earth, will glow with bright new suns and torn streamers of glowing gas, all twisting above and below the merging plane. The shape of the night will change forever. Right now, the Milky Way is a single calm band across our sky. During the merger, the band will tilt, fragment, and split. 2 glowing arcs will swing across the heavens at strange angles, slowly winding toward each other. The Sun and Earth, if they survive, will probably be flung into a new orbit far above or below the new plane of the combined galaxy, looking down on the carnage from a distance. Some scientists predict the Sun could be ejected from the combined galaxy entirely, drifting alone into intergalactic space, with the merged galaxy receding behind it like a shrinking lighthouse. Others think the Sun will simply settle into a new home in the suburbs of Milkomeda. Either way, our solar system is not just sitting in the galaxy, it is inside a bigger gravitational dance, and we have a partner already chosen. The merger is so far in the future that no living species on Earth today will see it, but the rehearsal has already begun. Andromeda is already bending the path of stars in our halo, far above and below the disk. The pull is real. The clock is set. Andromeda is not the only galactic neighbor. Zoom out one more level. The Milky Way and Andromeda live inside a small family of galaxies called the Local Group. It is a loose collection of more than 50 galaxies, all bound together by gravity, drifting through the vast empty space of the cosmos as a single unit. Most of them are tiny, faint dwarf galaxies, far smaller than the Milky Way. 2 members are giants. 3 or 4 members are medium-sized. The rest are the dwarfs, scattered like puppies around their parents. Each one of these neighbors sits at its own angle, above or below or around the plane of the Milky Way. The local group is not a flat disk. It is a clumpy, 3-dimensional cloud of galaxies, with our Milky Way near one end and Andromeda near the other. Some of the dwarf galaxies are very close. The Large and Small Magellanic Clouds, named after a 16th century explorer, hang just below the southern part of our galactic disk, like 2 faint smudges visible only from the southern hemisphere of Earth. The Large Magellanic Cloud is bound to the Milky Way and may have been on a long, plunging path toward us for billions of years. The Small Magellanic Cloud trails behind it, like a child holding a parent's hand. Both will eventually be torn apart and absorbed by our galaxy, joining the long parade of meals. Above the disk, hidden from the southern hemisphere, sits another group of nearby dwarfs: the Sculptor Dwarf, the Fornax Dwarf, the Sagittarius Dwarf already discussed. Each one has its own story, its own age, its own population of stars. Some have already been disrupted into streams. Others are still mostly intact, faint puffs of light that you would never see without a serious telescope. Here is the surprise. The local group itself is in motion. The whole family of galaxies is falling, as a unit, towards something even bigger. There is a massive concentration of galaxies sitting roughly 50 million light-years away in the direction of the constellation Virgo. It is called the Virgo cluster, and it contains over 1,000 galaxies. Our local group is being pulled toward it at hundreds of miles per second. We are not sitting still in space at any level. We are a planet on a star, on a galaxy, in a group, falling through the universe at almost incomprehensible speeds. And there is another pull. Beyond Virgo, even farther, sits an even larger gravitational well. It was named the Great Attractor by astronomers in the 1980s, when they realized something enormous was tugging on every galaxy in our region. The Great Attractor sits behind the dust of our own galactic disk, partially hidden from view. Many measurements still cannot fully see what is causing the pull. It may be a giant galaxy cluster. It may be something stranger. The exact identity remains unsettled. Whatever it is dragging us. Above and below our galaxy, the universe is sloped. We are sliding down a long, invisible hill, carrying our entire family of galaxies with us. The Milky Way is not the center of anything. It is just one passenger on a much longer journey, falling towards something we still struggle to name. Most of the universe is empty. When astronomers map the locations of galaxies on the very largest scales, a pattern appears. Galaxies are not scattered evenly. They line up in bright sheets and filaments, like soap bubbles standing edge to edge. Between the bubbles sit huge regions where almost nothing lives. No bright galaxies, no clusters, almost no light. These regions are called cosmic voids, and some of them are hundreds of millions of light-years across. We may be sitting near the edge of one. Several studies of galaxy counts in our region have suggested that the Milky Way and its local group lie inside a slightly underdense region of the universe, sometimes called the local void or the KBC void. Galaxies are sparser around us than they are in the average patch of the cosmos. Above and below the local plane, in directions outside the bright filament our local group belongs to, the dark stretches very far before the next sheet of galaxies begins. The local void itself is real. It is a region centered roughly above the disk of our galaxy, in the direction of the constellation Hercules. Inside it, very few galaxies have ever been detected. The void is at least 150 million light-years across, possibly larger. Anything sitting at the bottom of it would look out and see almost nothing in many directions, only thin, lonely galaxies far away. What makes voids interesting is not just their emptiness, it is what they imply. A void is a place where the gravity of nearby galaxies pulls outward on the matter inside. Anything near a void is being slowly tugged toward the bright filaments at its edges. Our local group is partly being shoved away from the local void, which is part of why we are falling toward the Virgo cluster. Imagine pouring a drop of water at the top of a giant, invisible bowl. The drop slides toward the rim. We are that drop. Our entire galactic family is sliding away from a quiet emptiness above us and toward a crowded richness below us. The push from the void is real. The pull from Virgo is real. Both are bending our path through the cosmos. There are bigger voids elsewhere, far above our galactic plane. In the direction of the constellation Eridanus sits one of the largest empty regions ever measured. Some studies have suggested it stretches across about 1 billion light-years, although the exact size remains debated. Inside it, the cosmic background radiation appears slightly cooler than in surrounding regions. Whether this cool spot truly marks a giant void or something more exotic is still unsettled. The mystery has not been closed. Below the disk, in the direction of the southern galactic pole, there are other voids, other emptinesses. Each one is a great hollow in the cosmic foam. Each one shapes the gravity field that drags on our galaxy. Here is the strange truth. Most of the volume of the universe is void, not galaxies. If you picked a random spot in the cosmos and stood there, you would almost certainly be inside one of these vast nothings, surrounded by nothing in every direction for further than light has had time to travel since the Big Bang. We got lucky. We are inside a galaxy, on a star, on a planet. Above and below us, the void is waiting. If our galaxy is a flat plate, then it has a top and a bottom, just like a coin. Astronomers have given those directions formal names. The direction perpendicular to the plate, sticking straight up out of one face, points to the North Galactic Pole. The opposite direction, sticking straight down out of the other face, points to the South Galactic Pole. Pick a clear night. Look up. The North Galactic Pole is sitting in a small, faint constellation called Coma Berenices, near the brighter stars of Leo and Virgo. There is no bright star marking the spot. The exact pole sits quietly in a patch of empty-looking sky, surrounded by faint, distant galaxies. Look in the opposite direction, on the other side of the sky. The South Galactic Pole sits in another faint constellation called Sculptor. Again, no bright star marks the spot. The pole is just a faint piece of sky, also full of distant galaxies. Why do these directions matter? Because when you look at either galactic pole, you are looking out of the disk of the Milky Way. You are looking through the thinnest part of the galaxy, with the least gas and the least dust between you and deep space. That makes the galactic poles the cleanest windows in our entire sky. Astronomers point their best telescopes at them when they want to see the most distant galaxies in the universe. Because looking anywhere else means peering through the foggy plane of our own galaxy. The famous Hubble Deep Field, a tiny patch of sky that revealed thousands of distant galaxies in a single image, was taken in a direction near one of these clearer windows. Looking through the galactic poles is like staring through the cleanest part of a windshield, while everything else is smeared with rain. Our solar system itself is currently sitting north of the galactic plane and slowly climbing higher. That means, right now, the North Galactic Pole is roughly the direction we are heading in terms of our slow vertical bobbing. We are not moving directly toward it, but we are climbing in that general direction. In about 13 million years, we will reach the highest point of our current bob, possibly 200 light-years above the plane, before gravity drags us back down. The South Galactic Pole, by contrast, points at where we will go after we cross back through the plane and dip below it, hundreds of millions of years from now. From our perspective today, it points down through the floor of our galaxy. Both poles are gateways to a much larger sky. Beyond them, hundreds of millions of light-years away, sit the great galactic clusters and walls. The Coma Cluster, holding more than 1,000 galaxies, sits not far from the North Galactic Pole. A lesser-known cluster called Fornax sits near the south. Looking up or down through these poles is the easiest way for our species to count the universe. And there is one more reason these poles fascinate astronomers. When the first true picture of our galactic neighborhood was made, mapping all the dust around the sun, the dust seemed to thin out faster in some directions than others. Above us, looking through the North Galactic Pole, the dust falls away into a strange, clean tunnel. The view is so empty that scientists believed for a while we lived inside an unusually clear local pocket. That clean tunnel turned out to be even more interesting than they thought. Close to the sun, in the direction of the North Galactic Pole, the gas and dust of our galaxy thin out in an unusual way. Astronomers call the feature the local chimney. The shape is exactly what the name suggests. Above us, a tall, narrow tunnel of low-density gas reaches up and out of the disk of the Milky Way, like the chimney on top of a house, opening to the empty space above the plane. A matching tunnel reaches downward through the floor of the galactic disk, opening to the empty space below. Together, these two tunnels turn the local bubble into something much weirder than a simple bubble. They turn it into a long, open shaft, with the sun sitting somewhere in the middle and the disk of the galaxy wrapped around it like the walls of a tower. Above us, the chimney rises hundreds of light years before it merges with the hot halo gas of the galaxy. Below us, it descends a similar distance before merging with the lower halo. The chimney is not solid air. It is mostly empty, even compared to the already thin local bubble. It is a hot, low-density tunnel through which energy and matter can leak from the galactic disk into the halo and back. Without these chimneys, the disk would trap most of its gas and heat. With them, the galaxy can breathe vertically, exchanging material with the halo above and below. How were the chimneys made? The current best explanation traces them to a cluster of supernova explosions. Many giant stars detonate together in a small region, and their combined shock waves carve out a cavity in the disk. The cavity grows so large it punches through the top and the bottom of the galactic plane, like a balloon bursting through both layers of a thin pancake. Millions of years later, the supernovae are gone, but the open shaft remains. The sun has wandered into one of these old shafts, possibly carved by stars that exploded long before life on Earth had crawled out of the sea. The implications are quietly enormous. The light we receive from very distant galaxies, when we look toward the galactic poles, comes through the chimneys. The cosmic rays hitting Earth from above and below come through the chimneys. The sun sits inside an unusually clear column of space, one of the best natural observatories in the Milky Way, and we did not know it existed in detail until very recently. Even more haunting, the chimneys are not symmetrical above and below. The northern chimney appears taller and wider in some maps than the southern one, suggesting the most recent supernovae that carved them detonated slightly above the plane rather than directly on it. Our sun is currently passing through this asymmetry, drifting upward, as if climbing toward the wide top of a slanted tower. Above us, beyond the chimney, lies the open sky of the galactic halo. Below us, beyond the southern chimney, lies the same. From our position, both directions show fewer stars than the band of the Milky Way, and that thinning is partly real and partly an illusion of the chimney. We are inside an empty column. Step back from the column, look at it from outside. There is something else flowing through the same direction, and it cuts our sky in half. Forget the galaxy for a moment. Come back to the page of the planets. There is something odd about that page itself. If you stand far from city lights, on a very dark night, just before sunrise or just after sunset, you can sometimes see a faint cone of glow rising from the horizon. It looks like the sky still holds a memory of the sun, a soft pyramid of light pointing up into the stars. The glow is not a sunrise. It is not a sunset. It is something else entirely. Astronomers call it the zodiacal light. It is sunlight reflecting off a flat sheet of dust that fills the inner solar system, lying squarely on the same plane as the planets. The dust comes from comets and asteroids, slowly grinding against each other and against the solar wind, leaving a thin haze of tiny grains. Those grains have built up a smooth disk that hangs around the sun like a faint halo, only visible from inside. From above the solar system, a cosmic visitor would see this dust as a glowing pancake, slightly thicker near the sun and tapering out around the orbit of Jupiter or beyond. From below, the same. From the side, the disk would look like a thin pencil line. We live inside that pencil line. The zodiacal light is the inside view. It is the only naked eye proof you can see, with your own face, that the solar system really is flat and that the page extends past the planets. Above and below the plane, the dust drops off sharply. Look straight up out of the plane and the sky goes black. Look along the plane and a faint glow stretches across it. Recent measurements with NASA's Juno spacecraft and other probes have suggested that some of this dust may actually be coming from Mars itself, blown off the surface by the solar wind and slowly spreading along the ecliptic. Other studies argue the dust comes mostly from short-period comets, dropping pieces every time they swing past the sundial. The exact source remains debated. The dust itself is not. We can map its glow. If you put a piece of this dust in your hand, you would barely see it. Each grain is smaller than a speck of soot. There are not very many in any given cubic mile. But because the dust spreads across hundreds of millions of miles of the solar system, it adds up to a faint but real glow. Here is what makes the zodiacal light haunting. It is the only part of the empty space inside our solar system that is not actually empty. Above and below the plane, there is far less of this dust. The pure vacuum begins almost as soon as you leave the disk. Our system is an illuminated pancake floating in a darker void, and we ride along its surface, oblivious, like ants walking across the lit dial of a watch we have never thought to look up from. The glow is fading. Over the course of human history, the zodiacal light has been one of the most reliable natural sights for stargazers. Light pollution from cities has erased it from view for most of the world. Many people alive today have never seen it once. It is still up there though. Above the page and below it, the solar system is brighter and stranger than your eyes have ever been allowed to know. Now back to the deep sky above and below the planets. Beyond Neptune, in the cold edge of our solar system, something strange is happening to the orbits of small, icy worlds. Astronomers have been mapping objects out there for decades. Most behave as expected. They orbit the sun in a wide range of paths, tilted at random angles, scattered by Neptune's gravity into the dark. But a small group of the most distant objects, the ones farthest out in the scattered disk and the inner Oort cloud, are doing something that should not be possible by chance. Their orbits are tilted in similar ways. Their long axes point in similar directions. They cluster, like compass needles, all leaning toward an invisible magnet. Two astronomers at Caltech, Konstantin Batygin and Mike Brown, were the first to argue strongly that this clustering is real and meaningful. In 2016, they proposed that the pattern is being shaped by an undiscovered planet, far out in the dark, much more massive than Earth, sitting in a tilted orbit above and below the plane of the inner planets. Its gravity, slowly tugging on the smaller bodies over hundreds of millions of years, would naturally pull their orbits into the lopsided pattern we see. They named the suspect Planet 9. If it exists, Planet 9 would be the most distant major world in our solar system. Estimates suggest it would orbit the Sun at a few hundred to over 1,000 astronomical units, taking somewhere between 10,000 and 20,000 years to complete a single lap. It would be much bigger than Earth, possibly the size of a small Neptune, perhaps 5 to 10 Earth masses. Its orbit would be tilted by tens of degrees from the plane of the planets, dipping above and below the page by huge distances over the course of every long, slow year. This is not confirmed. It is a theory, a serious, peer-reviewed theory, but still a theory. The same clustering pattern might be explained by something else, perhaps by the combined nudges of many smaller objects rather than a single planet, or perhaps by an observational bias, since we mostly see the bright, easy-to-spot members of the outer system. The honest answer is that we do not know yet whether Planet 9 is real. Searches are underway. Telescopes have been sweeping the sky for years, looking for a faint moving dot that might match the predicted path. The new Vera Rubin Observatory in Chile, only recently coming online, is expected to dramatically improve the search. Within a few years, Planet 9 will probably either be found or ruled out. If it is found, it will rewrite the textbook again. We would have to redraw the solar system to include a major world far above and below the orbit of every other planet, hidden in plain sight for the entire modern era of astronomy. Even more strangely, some scientists have proposed alternatives. Maybe what is out there is not a planet at all. Maybe it is a small primordial black hole, the size of a grapefruit but as massive as Earth, captured during the early days of the Sunday. Such an object would be invisible in normal light, betrayed only by its gravity. A planet we cannot see, a black hole we cannot rule out. Our outer dark is full of secrets that may finally be solved this decade. Long before Planet 9 was suggested, another strange world was found in the deep outer dark. The discovery shocked astronomers because the object had no business existing where it sits. The world is called Sedna, named after an Inuit goddess of the frozen sea. It was found in 2003 by a team that included Mike Brown, the same astronomer who would later argue for Planet 9. Sedna is roughly 600 miles wide, about the size of a small dwarf planet, and it has a deep red surface that some scientists think is the reddest natural color in our entire solar system. A strange tan color caused by ancient organic compounds baked by cosmic radiation for billions of years. What makes Sedna haunting is its orbit. Sedna takes more than 11,000 years to complete a single trip around the Sunday. Its closest approach brings it inside 76 astronomical units. Its farthest carries it out to roughly 900. For most of its long year, Sedna is so far away from the Sun that the light is too weak to do anything. The Sun would look like a slightly bright pinprick from Sedna's surface, no warmer or larger than a normal star. Here is the part that makes no sense. Sedna never comes close enough to Neptune to be flung outward by it. Whatever pushed Sedna into this lonely orbit was not Neptune. Neptune cannot reach that far. Sedna's path begins above and below the standard plane and stays in a region where no known force in the modern solar system should be able to set it. So where did Sedna come from? Three theories compete. The first says Sedna was placed in its orbit by a passing star that brushed close to our Sun billions of years ago when our solar system was still inside its birth cluster of stars. A close encounter would have flung small bodies onto wide tilted paths exactly like Sedna's. The second theory says Sedna was captured from another star system during the same close pass, born around a different sun and stolen by ours. The third theory says Sedna was pushed by Planet 9, the same hypothetical world that might explain the clustering of other distant orbits. All three theories are alive. All three remain unproven. Sedna is reaching its closest point to the Sun now, in our era. It will pass perihelion sometime in the next century or so, and then begin the slow climb back out into the deep dark. After that, no human will see Sedna again, for thousands of years. The next civilization to spot it, if there is one, will look at our records the way we look at ancient star charts, wondering what we knew and what we missed. A handful of similar worlds have been found since. Worlds called extreme trans-Neptunian objects. Each one has an enormous orbit. Each one tilts strangely. Each one fits the same odd pattern. They cluster like ghosts above and below the disk, possibly shaped by something we have not yet seen. Together, they are the inner edge of the Oort cloud made visible. They are the first hint that the wall of comets above us is real, and that something else might live among them. Sedna is the brightest of these visitors, a single window onto a quiet population that probably numbers in the thousands, all of them above and below the plane, all of them slowly drifting, all of them waiting their turn to fall. Now look up from the planets, past the comets, past the halo, all the way to the very center of the galaxy. Then look just above it and just below it. You will see two of the strangest structures ever found in our Milky Way. In 2010, scientists studying data from a NASA satellite called Fermi noticed something no one had expected. Above and below the center of our galaxy, two enormous lobes of gamma-ray light were glowing in the sky. Each lobe stretched roughly 25,000 light-years from the galactic center. Together, they reached 50,000 light-years from end to end, almost half the diameter of the entire Milky Way. The lobes were named the Fermi bubbles. They are nearly invisible to the human eye and almost invisible to most telescopes. Only in the highest energy light, gamma rays and X-rays, do they reveal their shape. They look like two enormous balloons, perfectly symmetric, growing out of the galactic core, one rising above the disk and one descending below it. Where did they come from? The leading explanation is that the Fermi bubbles are scars. Roughly 6 to 10 million years ago, the supermassive black hole at the center of our galaxy, Sagittarius A star, had a violent meal. Streams of gas fell into it. The black hole was unable to swallow all of the matter at once. It heated the surrounding gas and blasted out enormous jets of energy perpendicular to the galactic plane, above and below at the same time. Those jets carved the bubbles. They have been quietly glowing ever since. A different theory says the bubbles came from a burst of star formation in the central region. Many giant stars were born at once, lived fast, and died in supernova explosions that combined to push hot gas out of the disk. The blasts pushed up and down because the path of least resistance is perpendicular to the dense plane. Whichever theory is correct, one fact is settled. Our galaxy has a violent past. The center is not a peaceful place. Above us and below us, the wreckage of an event that happened before humans existed still glows in the sky. If your eyes could see gamma rays, you would not see the disk of the Milky Way as a quiet band. You would see two enormous bright balloons swelling above and below the galactic center, rising silently across the heavens. The image would be terrifying. The bubbles would dwarf every constellation. They would stretch from the southern horizon to the northern, from one celestial pole to the other. Sagittarius A star is mostly quiet today. It is a sleeping giant, 4 million times the mass of our sun, locked at the center of our galaxy. It eats only small snacks now, a stray cloud of gas, an unlucky star that wanders too close. But it has eaten violently before. The Fermi bubbles are proof. Above and below the disk, the past is still glowing. There is a quieter implication that should make us pause. If our central black hole erupted 6 million years ago, it can erupt again. Such eruptions are part of the slow life cycle of every galaxy. We do not know when the next one will come. We do not know how strong it will be. We only know that, in the great record above and below the plane, our galaxy has roared more than once, and the echoes never fully fade. Step back even farther, and you will see something almost no one in human history has thought about. Galaxies breathe. Above and below the disk of the Milky Way, gas and dust move on long, slow currents. The patterns are called galactic fountains. Inside the disk, hot gas rises out of star-forming regions, blown upward by supernova explosions and stellar winds. The gas climbs hundreds of light-years above the plane, cools as it rises, and then falls back down toward the disk as cold rain. The cycle takes tens of millions of years. The galaxy inhales and exhales, pumping warm gas up into the halo and pulling cold gas back down. We can actually see this rain when telescopes look at our halo in radio light. There are clouds of cold hydrogen falling toward the galactic plane from above, traveling at hundreds of thousands of miles per hour. Many of these clouds are too cold to glow in visible light. Astronomers have catalogued dozens of them. They are called high-velocity clouds. Some appear to come from the Magellanic Clouds. Some appear to come from other dwarf galaxies the Milky Way has eaten. Some appear to be condensed pieces of the hot halo itself, cooling and falling like droplets in a thunderhead. Our solar system is roughly 50 light-years above the galactic plane. Right now, we are sitting inside this slow rain. Some of the hydrogen falling toward our region of the disk may already be near the heliosphere. Most of it is so spread out that we cannot feel it as wind. But over millions of years, the rain adds up to enormous amounts of new fuel for our galaxy's star-making engine. This is how galaxies stay alive. Without fresh gas falling in from the halo, the disk would run out of fuel within a few billion years. New stars need new clouds. New clouds need replenishment. The breathing of the halo, above and below, is the lifeline that keeps our galaxy growing. A galaxy that has stopped breathing is called dead. Many giant elliptical galaxies have already reached this state. They are smooth, red, and quiet, full of old stars and very little new star formation. Their halos have stopped raining. Their fuel has been used up. The Milky Way is not yet in that state. The Milky Way still pulls in cold gas. The Milky Way still births new stars at a steady rate. Our home is alive, but the breathing is fragile. When two galaxies merge, the breathing can pause. When a black hole at the center erupts, like the one that carved the Fermi bubbles, it can shove the cool rain away from the disk and choke the cycle. After such events, the galaxy can take hundreds of millions of years to recover. There is a haunting thought hidden in this. The clouds raining down on the disk include atoms forged in supernovae from older generations. Some of those atoms came from stars that died before the sun was born. Some of them are now in your body. The carbon in your hand, the oxygen in your blood, the iron in your veins, the calcium in your bones, all of them came from stars that lived and died billions of years ago and rained their dust back down through the galactic halo. Above and below us, the rain has been falling for the entire history of our galaxy. We are made of it. Look at the band of the Milky Way on a dark night, and you will notice dark patches breaking it up. Those patches are not gaps in the stars. They are clouds of cold dust, blocking the light of everything behind them. The clouds are where new stars are being born. Star formation happens almost entirely inside the disk. Above and below the plane, the gas thins out fast, and the conditions for collapsing clouds become rare. But every now and then, a piece of the breathing rain we just talked about pulls together enough mass to form new stars, even outside the main disk. Closest to home, an enormous filament of cold gas was recently mapped near our sunday. It is called the Radcliffe Wave, named after the institute that found it. The Radcliffe Wave stretches roughly 9,000 light-years, longer than any star-forming structure ever previously identified, and it ripples gently above and below the galactic plane like a wave on water. Our sun is sitting just below one of its peaks, and most of the famous nearby star nurseries, including Orion, Taurus, and Perseus, are part of this single great wave. Until 2020, no one knew these regions were connected. Astronomers had mapped each nursery separately for over 100 years. The Hubble telescope had photographed them. Generations of children had memorized their names. Nobody had realized that all of them were beads on the same string. The wave was found using new measurements from the Gaia Space Telescope, which mapped the precise positions of more than 1 billion stars in our galaxy. When the data was processed, the wave appeared like a hidden serpent, undulating through our local neighborhood. Where it dips below the plane, gas piles up into clouds where stars can form. Where it rises above, the same. The sun probably crosses this wave or one like it many times during its slow vertical bobbing through the disk. Each crossing brings us close to active star-forming regions, with all the radiation, supernova risk, and gas density that comes with them. The crossings might explain past variations in cosmic ray exposure on Earth. Some scientists have proposed that the wave, or older versions of it, may even be linked to mass extinctions. The idea is unproven, but the wave itself is real. Beyond the Radcliffe Wave, there are other nurseries above and below the plane. The Magellanic Stream, a long ribbon of gas trailing the Magellanic Clouds, drags below the southern part of the galactic disk and could feed future star formation when the gas eventually settles. Some star clusters appear to form in the halo itself, born from the high-velocity clouds raining down from above and below the plane. The youngest stars in the galaxy are born in the disk and stay close to it. They have not yet had time to drift. The oldest stars, by contrast, have wandered everywhere. A halo star is allowed to be far above or below the plane because it has had 10 billion years to climb out of any orbit. The youngest stars hug the page. The oldest stars float free. If a baby star is born today inside a cloud that hangs above the plane, that star will spend its early life looking down on the disk of the Milky Way as a glowing pinwheel below it, with most of the stars sitting in a thin layer beneath its feet. Such planets would have a different sky. The Milky Way would not be a band, it would be a ceiling or a floor, depending on which way they faced. Above and below us, all the time, an invisible storm is falling. The storm is made of cosmic rays. These are not really rays. They are tiny particles, mostly the cores of atoms, traveling at almost the speed of light. They rain down on Earth from every direction, day and night, in clear weather and in storms. Several thousand of them have passed through your body since you started reading this chapter. None of them harmed you, because the atmosphere and the heliosphere together blocked most of the dangerous ones, and your body shrugged off the rest. Where do cosmic rays come from? The lower energy ones come mostly from the sunday. The sun is constantly burping out streams of charged particles, especially during solar storms. Those particles are dangerous to astronauts and spacecraft, but the Earth's magnetic field, combined with the atmosphere, shields the surface. The medium energy ones come from supernova explosions inside the Milky Way. When a massive star dies, it accelerates particles to enormous speeds. Those particles bounce around in the magnetic fields of the galaxy for thousands or millions of years before reaching us, often arriving from above or below the plane after long journeys through the halo. The highest energy ones are still a mystery. They arrive at our planet with energies hundreds of millions of times greater than anything humans can produce in particle accelerators. Some of them carry, in a single subatomic particle, more energy than a baseball thrown by a major league pitcher. Where they come from is not fully known. Many appear to arrive from above the galactic plane, suggesting their source is outside our galaxy entirely. Some leading theories point to active galaxies with feeding supermassive black holes, possibly hundreds of millions of light years away. The very highest energy event ever recorded was nicknamed the Oh My God particle. It was detected over the Utah desert in 1991. A single proton, accelerated to almost unimaginable speed, struck the upper atmosphere with enough energy to glow visibly to instruments on the ground. The particle had been traveling for a long time before it reached us. Its origin remains unknown. This rain is happening above and below our solar system right now. Cosmic rays are not blocked by any single planet, any single star, or even any single galaxy. They thread through the universe almost everywhere. Our heliosphere weakens them, our atmosphere absorbs them, our magnetic field deflects them. Together, these three shields protect every living thing on Earth. If the heliosphere shrank, cosmic rays would increase at the surface. If the atmosphere thinned, they would increase further. If Earth lost its magnetic field, even more would slip through. Each shield is doing important work, every second, in directions you cannot see. There is a strange beauty in the fact that the rain falls equally from above and below. The galaxy has no preferred direction for these particles. Whether they arrive from the North Galactic Pole or the South, from a constellation overhead or from one beneath the floor of the world, they hit Earth in roughly equal numbers. Our planet is held inside an even shower, and the soft glow you sometimes see in the upper atmosphere, the auroras, are partly the visible signs of this storm being deflected by our magnetic field. The storm has been falling for as long as Earth has existed. It will keep falling for as long as the galaxy keeps stars. There is something else falling on you all the time. Something far stranger than cosmic rays. Something so quiet that you cannot feel it, see it, hear it, taste it, or detect it with any of your senses, and yet it almost certainly outweighs all the visible matter in the universe by more than 5 to 1. It is called dark matter, and it is everywhere above and below the disk. Dark matter does not glow. It does not absorb light. It does not bump into ordinary atoms in any way we can directly notice. It interacts with the rest of the universe only through gravity. We know it is real because we can see what its gravity does. The stars on the outer edge of every galaxy, including the Milky Way, move much faster than they should, given the visible mass we can see. There is far more pull on them than the bright stars and gas can provide. Something invisible, something heavy, must be there, holding the galaxy together. Without it, every spiral galaxy would fly apart in a few rotations. Most of the dark matter in the Milky Way lives in a vast halo that extends far above and below the disk. The halo is roughly spherical, much wider and deeper than the visible part of the galaxy. It surrounds us like a giant transparent ball, with the disk of bright stars sitting like a thin coin floating inside it. Right now, you are sitting inside that ball. Dark matter particles are moving through your body, through the walls of the room you are in, through Earth itself. The best estimates suggest about 1 billion such particles are passing through your body every second. None of them stop, none of them push. They simply pass, the way light passes through clear glass, invisible and unfelt. Experiments deep underground in old mines and abandoned tunnels have been hunting dark matter for decades. They sit shielded from cosmic rays, watching for the rare possible flash of a single dark matter particle bumping into a normal atom. So far, no confirmed direct detection has been made. The candidates remain candidates. The leading suspects are weakly interacting massive particles, sometimes called WIMPs. Other candidates include axions, sterile neutrinos, and primordial black holes. Each suspect has its own theory. Each has its own searches. None has been pinned down. Dark matter remains one of the largest unsolved problems in physics. Here is the unsettling part. Even though we do not know what dark matter is, we can map where it is. The maps show structure. Above and below our galaxy, dark matter is not smooth. It has clumps, streams, and possibly long filaments running through the halo. Some computer simulations suggest that dark matter may form long, thin filaments connecting our galaxy to neighbors. These filaments would stretch above and below the plane like invisible ropes, threading through the cosmic web. Our solar system may right now be inside one of these filaments. We may be falling along one. We may be sitting on a quiet bridge of invisible matter stretching from our galaxy to Andromeda. We have no way yet to tell from inside. The whole sky above us and the whole space below us is full of mass we cannot see. We have only a glimpse of its outline, drawn from the way it curves the paths of light and stars. The bigger picture is still being built, slowly, by every new telescope, every new underground detector, every new bit of data. Now, look out, far above the disk, far below it, in any direction you choose. Almost every galaxy you can imagine has a giant secret at its core, a supermassive black hole. Our Milky Way has Sagittarius A star, weighing about 4 million suns. Andromeda has one even bigger, weighing roughly 100 million suns. The galaxy at the center of our local group's nearest cluster, Virgo, contains a black hole that the Event Horizon Telescope photographed in 2019. It weighs about 6.5 billion suns. That black hole, hosted by the galaxy M87, was the first ever directly imaged. The image looked like a blurred orange donut surrounding a bottomless central darkness. Above and below the plane of our own galaxy, dozens of nearby galaxies hold their own supermassive black holes, Some are quiet, like ours. Some are eating, glowing fiercely as they swallow gas. The ones that are eating are called active galactic nuclei, and the brightest of them, called quasars, can outshine an entire galaxy of stars from a single point smaller than our solar system. These quasars are visible from billions of light years away. Some of the most distant ones we can see are so far away that their light has been traveling toward Earth for nearly the entire age of the universe. When you look at a distant quasar, you are looking at a black hole eating in a galaxy that probably no longer exists in the same form. Its glow has been on its way to your eyes since before the Earth was born. Many of these galaxies sit in directions roughly above and below the Milky Way's plane, simply because the dust of our own disk gets in the way when we look along it. Looking through the galactic poles, telescopes catch these distant monsters more clearly. The cleanest views of supermassive black holes feeding outside our galaxy almost always come from looking up out of our disk or down through it. Some active black holes shoot out enormous jets of matter, perpendicular to the spinning disk of gas around them. Those jets can extend for hundreds of thousands of light years in a straight line, longer than the host galaxy itself. From far away, the jets look like glowing spears piercing the darkness. The black hole at the heart of M87 has one of the most famous of these jets. It has been visible to telescopes for over a century, long before anyone knew what it was. Each jet is launched along the spin axis of the black hole, which means each jet points either above or below the plane of the disk that surrounds it. Galaxy by galaxy, all over the universe, the same pattern repeats. Spinning disk, up jet, down jet. The cosmos is full of these structures. Above us and below us, jets are firing constantly, somewhere in some galaxy, every moment of every day. The implication, when you sit with it, is enormous. Every galaxy has a center. Every center has a giant. Every giant rules a region of space far above and below the local disk. The Milky Way is not unusual. We are one of billions of households, each with its own caged giant in the basement, each tending its own quiet flame. And in the very early universe, those flames were brighter. The young cosmos was a wilder place, full of bigger meals and faster eating. Looking out and up into the deep dark, we are looking back into that earlier time. Pull back even further. Imagine you can see the whole observable universe at once. The galaxies are not scattered randomly. They form a pattern. Astronomers call it the cosmic web. On the largest scales, galaxies line up in long, thin filaments, stretching for hundreds of millions of light years. The filaments connect at thick knots, where galaxy clusters live. Between the filaments sit the great voids, where almost nothing lives. The filaments and voids together form a structure that looks remarkably like the inside of a sponge, or like the foam on top of a glass of beer, with the bubbles being voids and the walls between them being filaments. Above and below our local group, the cosmic web is in full view. Long, bright filaments curve away from us in many directions. The Virgo cluster sits along one of them. The Coma cluster sits along another. The Hercules supercluster sits farther still. Each one is a knot in the great network. Each one is connected to the others by invisible threads of dark matter and thin streams of gas, channeling galaxies along their lengths like ants on a vine. The Milky Way and the rest of the local group sit on a piece of one of these filaments. Our small home cluster appears to be part of an even larger structure called the Laniakea supercluster, mapped in 2014. Laniakea, a Hawaiian word meaning immense heaven, contains roughly 100,000 galaxies and stretches across more than 500 million light-years. We are a tiny corner of it. Even Laniakea is just one of many superclusters in the observable universe. The cosmic web extends in every direction, repeating the same foamy pattern out to the edge of what we can see. The pattern continues above the plane of the Milky Way. The pattern continues below it. The pattern continues out to the very edge of the cosmos. The strange part is how this pattern formed. In the first fraction of a second after the Big Bang, the entire universe was nearly uniform. The matter was almost evenly spread. with only tiny ripples of slightly higher and slightly lower density. Those tiny ripples, magnified by the gravity of dark matter over billions of years, grew into the cosmic web we see today. Slightly denser regions pulled in more matter, became filaments, and grew galaxies. Slightly emptier regions pushed matter out, became voids, and stayed dark. Every galaxy you see, every filament, every cluster, every supercluster, is the slow result of those whispered fluctuations from the earliest microsecond of time. The shape of the universe today is a fossil of conditions that existed long before any star was born. Above us and below us, the pattern is still growing. New filaments are still feeding old clusters. Old galaxies are still being pulled along the threads. The web is alive in slow motion. If you could speed up time by 1 billion times, you would see galaxies sliding along the filaments toward the great clusters, dropping into the knots like beads on a string, while voids slowly grow emptier between them. The cosmic web is the largest structure ever known. Nothing bigger has been measured. Whether anything bigger exists depends on the geometry of the universe itself. So far, the web appears to fill space evenly, with no hint of an even larger pattern containing it. From our position on a thin Earth, on a small star, in a small galaxy, in a small group, on a small filament, we see a structure that may have no larger frame. There is a wall around us that no one ever talks about. It is not a physical wall. It is a wall made of time. We call it the edge of the observable universe, and it sits in every direction above and below us, exactly the same distance away. The reason the wall exists is simple. Light travels at a finite speed. The universe began about 13.8 billion years ago, in the event we call the Big Bang. Light from any object can only have been traveling toward us for at most 13.8 billion years. Anything farther away than that has not had enough time for its light to reach us yet. We cannot see it. We may never see it, because the universe has been expanding for that whole time. The practical edge of what we can observe is even farther than 13.8 billion light-years away. The actual radius of the observable universe is roughly 46 billion light-years in every direction. Above us, below us, in every constellation, the edge sits the same distance away. We are at the center of our own bubble of vision, and so is every observer everywhere else. When you look up at the sky and stare in any direction long enough, you are eventually looking at the wall. Most galaxies are well inside it. The most distant galaxies our telescopes have found are very close to the wall, glowing faintly with light that has been traveling toward us for over 13 billion years. At the very edge sits the cosmic microwave background. This is the faint glow of the universe itself when it first became transparent, about 380,000 years after the Big Bang. Before that, the universe was too hot and dense to be transparent. Light could not freely travel. When the universe finally cooled enough, the trapped light was released. That ancient light has been traveling ever since, and now it fills every direction of our sky as a soft, almost perfectly even glow in the microwave part of the spectrum. If your eyes could see microwaves, the entire sky above and below you would glow steadily, not brilliantly, but evenly. The glow would have no source. It would simply be there. The whole universe, looking back at you from the moment it became transparent. Telescopes have mapped this glow in stunning detail. The maps reveal tiny variations in temperature, the same ripples that later grew into galaxies and voids. Looking at those maps is the closest we can get to seeing the early universe with our own eyes. They are baby pictures of the cosmos. Beyond the cosmic microwave background, no light has ever reached us. Whatever is out there is not part of our observable universe. Some of it may be physically real, simply too far away for its light to have arrived yet. As time goes on, more of it will become visible to future generations, although the expansion of the universe is also pulling much of it permanently out of reach. There is a horizon beyond which nothing will ever be seen, no matter how long we wait. Above us, below us, and in every direction, the wall of time stands at the same distance. Our universe is bigger than what we can see, but the visible part is already vast beyond comprehension. Almost 2 trillion galaxies live inside the bubble. Each galaxy has hundreds of billions of stars. Each star may have planets. Each planet may have its own sky, and yet none of them, anywhere, can see beyond their own walls of time. Now zoom inward, all the way back to the beginning. The Big Bang was not a quiet birth. The current best theory says that, in the first tiny fraction of a second, the universe expanded faster than light, faster than anything has any right to travel. The expansion was so violent and so brief that the universe doubled in size dozens of times in less than a single trillionth of a second. The theory is called cosmic inflation. It was proposed in 1980 by physicist Alan Guth and developed by many others in the years that followed. Inflation explains several stubborn puzzles. It explains why the universe looks so smooth on large scales. It explains why the cosmic microwave background has nearly the same temperature everywhere, even in patches that should never have been able to communicate with each other. It explains why we do not see strange leftover particles called magnetic monopoles, which simpler models predict. During inflation, tiny quantum fluctuations in the fabric of space were stretched to huge sizes. Those stretched fluctuations became the seeds of every galaxy, every cluster, every void, every star, including our Sunday. The pattern of dust above and below the disk of the Milky Way, the locations of every galaxy in our halo, the cosmic web itself, all of these large structures trace their origin to those random ripples blown up by inflation. Inflation also predicts something more disturbing. It does not have to stop everywhere at the same time. In some versions of the theory, called eternal inflation, the inflating region keeps expanding faster than the rate at which it slows down anywhere within it. Pockets stop inflating and become normal universes like ours. Outside those pockets, inflation continues forever. The implication is that our entire observable universe may be a single bubble inside an endlessly inflating sea of other bubbles. Each bubble could be its own universe, with its own physical laws, its own constants, its own histories. Our universe may be one of an infinite series of separate cosmos, each with stars or no stars, life or no life, time or no time. Above us and below us, beyond the wall of light, those other bubbles may be expanding silently, forever. This is not a confirmed picture. Eternal inflation is a serious idea, taken seriously by many physicists, but it remains a theory. We have no way to observe other bubbles. They are outside our reach by the very nature of the model. Whether they exist may be a question we can never answer experimentally. What is on firmer ground is regular inflation, the brief explosive expansion in the first instant of time. The cosmic microwave background carries fingerprints that match its predictions. The pattern of galaxies on the largest scales matches its predictions. New experiments in the polarization of the microwave background are still searching for the very first signal of inflation, the gravitational waves it would have produced. So far, the search has not found a clear signal. The hunt continues. Whether or not multiple bubbles exist, the lesson of inflation is unsettling enough on its own. Everything we see, every galaxy above us and below us, every star in our halo, every grain of dust in our heliosphere, every atom in your body, came from a brief explosion of space itself, from a pattern of microscopic fluctuations stretched to cosmic size in less than a flicker of time. We are the slow children of a fast moment. There is a different kind of signal pouring through the space above and below us. It does not travel as light. It does not travel as particles. It travels as ripples in the very fabric of space itself, gravitational waves. When two massive objects spiral together and collide, like two black holes or two neutron stars, they shake the structure of space around them. The shaking spreads outward at the speed of light, stretching and compressing every distance it passes through, very slightly. The effect is real, but tiny. By the time a gravitational wave reaches Earth from a distant collision, The stretching changes the length of a kilometer by less than the width of a single proton. For decades, we could not detect such small distortions. In 2015, that changed. The LIGO Observatory, with its twin instruments in Washington and Louisiana, picked up the first confirmed signal of two black holes colliding more than 1 billion light-years away. Each black hole was about 30 times the mass of the Sunday. They had been spiraling toward each other for millions of years. In the final fraction of a second before they merged, they released more energy than all the stars in the visible universe combined, all of it in the form of gravitational waves. The signal lasted less than half a second. It came from above the galactic plane, from a direction in the southern sky. In that half second, our planet stretched and squeezed by an amount no human could feel, but the instruments noticed. The wave was real. The age of gravitational astronomy had begun. Since then, dozens more events have been detected. Black holes colliding, neutron stars colliding. In 2017, one such neutron star merger was detected both in gravitational waves and in light, allowing astronomers to identify the source galaxy. The collision created a killer nova, a brief explosion that produced gold, platinum, and other heavy elements. Some of the gold in your jewelry may have come from a similar event billions of years ago in another galaxy that no longer exists in the same form. Above and below us, the universe is constantly humming with these waves. Most are too faint to detect. The strongest, from the largest mergers, ripple through the planet a few times a year now, and the rate of detection is rising as new observatories come online. A new effort, called pulsar timing arrays, is hunting for waves at much longer wavelengths, the kind produced by supermassive black holes spiraling toward each other in the cores of merging galaxies. These waves can stretch across years rather than seconds. In 2023, the first hints of a continuous background hum from such mergers were announced. The hum, if confirmed, is the combined whisper of every supermassive black hole pair across the universe. A slow chord rising from below the sky and from above it, in every direction at once. This is one of the most exciting developments in modern astronomy. A new sense, opened just within the past decade, listening to the universe in ways nobody had ever listened before. Every collision sends a ripple. Every ripple eventually reaches us. Above and below the disk of our galaxy, the cosmos has been ringing for billions of years, and now we can finally hear it. The space around our planet is not silent. It is humming. We just had to learn how to listen. Look forward in time, far past the lifetime of any human civilization. The universe has a likely future. The future is colder, darker, and emptier than anything alive today can fully imagine. The current data, collected over decades of observations, suggests that the expansion of the universe is accelerating, not just continuing, speeding up. Distant galaxies are pulling away from us faster every year. Whatever is driving this expansion has been called dark energy. Like dark matter, we do not know what it is. Unlike dark matter, it appears to be everywhere evenly, filling every cubic foot of space with a tiny push outward. If dark energy continues to behave the way it does now, the long-term fate of the universe is settled. The acceleration will continue. Galaxies that are not gravitationally bound to ours will recede faster and faster until eventually they pass the cosmic horizon and vanish from our sky entirely. The local group will hold together. Andromeda and the Milky Way will eventually merge. The other 100 billion galaxies will all fade from view. Hundreds of billions of years from now, the only galaxies visible in any direction above or below the merged Milkomeda will be the ones that were already gravitationally bound to it. The rest of the universe will be too far away. Any scientists living in that distant era, if any exist, will look up and see a far smaller cosmos than we see today. They might never know that the great cosmic web ever existed. They might never discover the Big Bang. The story does not end there. The remaining galaxy will eventually run out of fuel for new stars. The final generation of stars will burn out. The longest-lived stars, Small red dwarfs can keep glowing for trillions of years, but even they have an end. After roughly 100 trillion years, the last stars will fade. After that comes the long darkness. White dwarfs, the burnt-out cores of medium stars, will slowly cool. Black holes will sit in silence, occasionally swallowing stray bits of matter. The universe will be black almost everywhere, with only the faintest infrared glow from the dying remnants of stellar corpses. The temperature will drop toward absolute zero, with only tiny gravitational and thermal fluctuations remaining. Even black holes will not last forever. According to the theory of Hawking radiation, proposed by physicist Stephen Hawking in 1974, black holes very slowly leak energy and shrink over enormous timescales. The smallest black holes evaporate fastest. Supermassive black holes evaporate the slowest, taking on the order of 10 to the 100th power years to fully disappear. After all of them are gone, the universe will be a thin sea of low-energy particles drifting through near-perfect cold. This is sometimes called the heat death of the universe. Above us, below us, in every direction, the cosmos will be effectively over. There will still be space. There will still be time. There will be no structure, no life, no light, no event of any meaning. This future is far away. The longest scales of stellar existence still lie ahead of us. Civilizations could rise, fall, and rise again countless times before the night arrives. But the night is coming. Some physicists have proposed alternatives. Maybe dark energy will reverse. Maybe a new Big Bang will start a new universe somewhere. Maybe the cosmos will cycle. None of these alternatives are confirmed. The default forecast remains the slow fade. Now, back home, to the unsolved puzzles right above and below our planets. Earlier we mentioned a strange alternative to Planet 9. It deserves a closer look, because if it is real, it is one of the eeriest things ever proposed in our solar system. A small black hole. Most black holes form when massive stars die. Their masses run from a few times the mass of the Sun on up to billions. They are not subtle. They glow when they eat. They warp the orbits of nearby stars in obvious ways. Nothing like that lives anywhere near our solar system. We would have noticed long ago. But there is another kind. Primordial black holes, theorized to have formed in the first instant of the Big Bang, before any stars existed. Tiny, dense regions of the early universe could have collapsed directly into black holes of any size, including very small ones, smaller than any stellar mass. A primordial black hole with the mass of Earth would have an event horizon roughly the size of a marble. It would be black, silent, and almost impossible to detect except by its gravity. In 2020, two physicists, Jakob Schultz and James Unwin, proposed something startling. They argued that the strange clustering of orbits in our outer solar system, the same clustering that suggested Planet 9, could just as easily be explained by a captured primordial black hole. The numbers fit. A black hole of the right mass, in the right orbit, would tug on the distant icy worlds in exactly the way Planet 9 would, but it would emit no visible light at all. If such an object exists, it has been orbiting our Sun for billions of years, possibly captured from interstellar space when our solar system was young and crowded. It would have a mass of several Earths, but a body the size of a piece of fruit. Around it, a small cloud of dark matter might collect, occasionally interacting with itself and producing very faint gamma rays. Some scientists are now searching old gamma ray data for hints of exactly this signature. Nothing has been found yet. The idea remains a theory. Most astronomers consider an actual planet a more likely explanation than a captured black hole. But the black hole hypothesis is plausible enough that it cannot be dismissed without evidence. If a tiny black hole really is sitting in our outer solar system, what would it look like up close? It would not look like anything. It would be a perfectly black sphere, a few inches across, surrounded by a small region where light bent around it. From a distance of a few miles, your eyes would see a disturbance against the background stars, like a glass marble distorting a star field. Closer in, you would see the strangest sight in our cosmic neighborhood. A pinprick of perfect darkness, with a ring of distorted starlight curling around it. If you fell in, you would be torn apart by tidal forces, your body stretched to threads in the final seconds before crossing the event horizon. After that, no signal from you would ever escape. The Vera Rubin Observatory, the same instrument that may finally settle the question of Planet 9, might also turn up indirect evidence for this weirder alternative. Within the next few years, we may know whether a piece of the early universe has been quietly orbiting our sun for the entire history of life on Earth. Most pictures of the solar system show it as a circle, with the sun in the middle, but our system is moving, and a moving body in space leaves a wake. Our wake stretches behind us like the tail of a comet, far below and behind the planets, in a direction most people have never even thought about. Astronomers call it the heliotail. Remember the heliosphere, the great teardrop bubble of solar wind that contains our entire solar system. The teardrop has a nose, where it pushes against the gas of the local interstellar cloud, and a tail, where it streams away on the downwind side. The nose is rounded and short. The tail stretches for a much longer distance. It may extend many tens of times the diameter of the heliosphere itself. Inside the tail, the solar wind continues to flow outward, but it is no longer being shaped by the pressure of the interstellar medium pushing back. The plasma slowly cools. It drifts. Over enormous distances, it eventually loses its identity and merges with the interstellar gas behind us. NASA's Interstellar Boundary Explorer, called IBEX, has been mapping the edges of the heliosphere for over a decade. Its observations have confirmed that the heliotail exists and that it has a complex shape with two pairs of lobes, one set above and below the central axis. The lobes appear to be sculpted by the sun's magnetic field, which twists outward in a spiral pattern as the sun rotates and the solar wind flows. From far above the solar system, our heliosphere would look like a glowing teardrop with a long, fluttering tail behind it. Inside the tail, the structure resembles a four-leaf clover, with two faster-moving lobes and two slower ones. The pattern is unique to our particular star, our particular wind, and our particular speed through the interstellar medium. The downstream direction of the tail points roughly toward the constellation Pisces, well below the plane of the planets and behind the orbit of Earth. If a traveler were to follow our tail outward, they would leave the solar system in a direction nearly opposite to Voyager 1, which exited through the upwind side of the bubble. The tail is longer than the path Voyager has taken so far. We do not yet know exactly how long, but estimates suggest hundreds of astronomical units, at minimum, and possibly thousands. Inside the tail, things may be quietly moving, particles from the Sunday, tiny grains of dust caught in the flow, possibly even visiting interstellar particles funneled into the wake by our magnetic field. Some scientists have suggested the tail may serve as a kind of corridor, channeling material between our system and the interstellar medium beyond. What lies beyond the end of the tail? Nothing dramatic. The plasma we sent out becomes indistinguishable from the gas of the wider galaxy. Our wake fades. We pass into the interstellar medium without ceremony. There is something quietly moving about this image. Our solar system, viewed from outside, is not a static picture, but a moving teardrop, leaving an invisible trail behind it. We have been doing this for billions of years. Every star you see is doing the same. Each one a teardrop, each one a tail. The galaxy is full of these silent wakes, crisscrossing each other, weaving through the local clouds like a forest of slow comets. We are one of them, drifting through our own faint trail, oblivious to the wake we leave above and below us. A world does not need a sun. For most of human history, people assumed every planet must orbit a star. The idea seemed obvious. Planets formed in spinning disks around young stars, so they should be locked to those stars by gravity. The picture matched our solar system. 8 planets, all bound to the Sunday. The picture turned out to be incomplete. Over the past decade, astronomers have found growing evidence of free-floating planets, also called rogue planets, drifting through the galaxy without any star to call their own. These worlds were either ejected from their birth systems by gravitational interactions or formed in isolation in collapsing clouds too small to make a star. Either way, they now wander the dark, drifting alone among the constellations. Some of these rogues are huge, the size of Jupiter or larger. Some are smaller, possibly the size of Earth. The smallest are very hard to find because they emit almost no light. They are detected mostly by gravitational lensing, when their gravity briefly bends the light of a more distant star and causes it to flicker for hours or days. Patient surveys have spotted dozens of such events. Each one suggests a hidden world drifting between the stars. Recent estimates suggest that the number of rogue planets in the Milky Way may exceed the number of bound planets. There may be more lonely worlds out there than ones with suns. Many of them sit far above and below the galactic disk, having been flung out of their original systems by close encounters with siblings billions of years ago. Many more drift in the disk itself, mixed in with the stars but unattached to any of them. It is statistically very likely that one or more rogue planets are passing close to our solar system right now. They would need to be quite close before any telescope could spot them. A rogue Earth at the distance of the Oort cloud would be almost impossible to detect with current instruments. Only the largest, brightest rogues, with self-glowing surfaces from internal heat, can be seen at interstellar distances. Some scientists have even speculated about rogue moons. If a giant rogue planet held onto its moons during ejection, those moons might still orbit it, warmed by tidal forces or by the leftover heat of the planet itself. Subsurface oceans on such moons could remain liquid for a very long time. Life, if it ever existed there, might persist in the dark, far from any sun. We have no proof of such life. We have no proof of any such moons, but the possibility cannot be dismissed. The galaxy is large. Rogue worlds are common. Above and below the disk, away from any star, the dark may be quietly inhabited in places we cannot yet see. A rogue planet might also be the explanation, or part of the explanation, for some of the strange orbital perturbations seen in our own outer solar system. If a rogue passed within a few thousand astronomical units of our Sun in the recent geological past, it could have stirred the Oort cloud or disturbed the tilts of distant icy worlds. There is no direct evidence of such a passage, but the math allows for it. The solar system above us and below us is not as closed off as our textbooks suggest. The space between stars is full of moving objects. Some are tiny dust grains, some are stray comets, some are entire worlds. Every one of them is a possible visitor to our quiet corner. We have come a long way, from the flat page of the planets, up through the icy shell of the Oort cloud, past the heliosphere, through the local interstellar fog, across the galactic plane, into the halo, beyond the local group, along the cosmic web, all the way out to the wall of light at the edge of the visible universe. And we have come back down, through the breathing rain of the galaxy, into the strange orbits of unseen worlds that may sit just beyond Pluto, into the silent wake of our own solar system as it falls through the dark. Tonight, when the sky is clear, look up. Then think about what you cannot see. You cannot see the trillions of icy mountains in the Oort cloud above your head and below your feet. You cannot see the heliosphere wrapping around the sun like a teardrop. You cannot see the interstellar fog the sun is drifting through. You cannot see the chimney of cleared gas reaching above and below us through the disk of the Milky Way. You cannot see the breathing of the galaxy, the rain of cold hydrogen falling toward the disk. You cannot see the streams of stars from Eaton dwarf galaxies looping through our halo. You cannot see Andromeda falling toward us. You cannot see the cosmic web, the great filaments and voids stretching across the visible universe. You cannot see the wall of microwave glow at the edge of your sky. You cannot see the gravitational waves rippling through the room you are sitting in. You cannot see the dark matter passing through your body. All of it is real. All of it is there. The flat page of the planets is the smallest part of the picture. The empty space above and below it is where most of the universe actually lives. Our textbooks have spent 2 centuries teaching one quiet diagram. The truth is, a 3-dimensional ocean, layered with bubbles, currents, ribbons, and shells, each one larger and more complex than the last. We are passengers on a small star. Our star is a passenger on a large galaxy. Our galaxy is a passenger on a cosmic web that may itself be a passenger inside something we cannot see. Each layer of the journey involves directions our ancestors did not have words for. Up out of the disk, down through the floor, above the plane, below the plane, northern halo, southern halo, Pisces tail, coma pole, sculptor pole. The names are scaffolding. The reality is a dense, living architecture of matter and energy, surrounding us in every direction at every moment. There is no edge to the night that does not deserve attention. Above your head, somewhere in the dark, a comet from the outer Oort cloud is just starting its slow plunge toward the Sunday. Below your feet, somewhere through the Earth and out the other side, gravitational waves from a black hole collision 1 billion years ago are passing through the planet now. To your left and right, dark matter is pouring through the room. Above the galactic plane, an old halo star is finishing one more long orbit. Below the disk, a stream of debris from the Sagittarius dwarf galaxy is still drifting outward, 600 million years after its first plunge. Look up, look through, look past. There is so much more above and below us than the dayside ever shows. The next time someone tells you what space is like, ask them which direction they are pointing.